All right, so 2-5 logarithms. This would be, 5-5 in the textbook here. We're going to just define what a logarithm is today and looking at evaluating them, all right? Now, if you look at the top here, it says, let's begin by watching a video about logs. We're kind of on a shortened period today, so we're not going to do that. So let's just talk about what a log is. So far, we've been looking at exponential functions, right? So here we have the exponential function f equals b to the power of x. We know that's 1 to 1, which means it would have an inverse, right? To find the inverse of it, you would switch the x and the y. Okay, so f becomes x, and then x becomes y. And that leads us to this equation. We always want our equation solved for y, right? We think of y as the dependent variable and x is the independent variable. Well, currently, we have that opposite. We have x is independent, y is dependent. So when y is up there as an exponent, it's like how do we solve for y? Okay? Well, that's where a logarithm comes into play. All right, we say the logarithmic function to the base b, where b is greater than 0 and cannot equal 1, is denoted by y equals log base b of x. And that is considered equivalent to what we came up with the inverse to this exponential. It's equivalent to x equals b to the power of y. Notice how we read that. We say y equals log base b of x, or the logarithm to base b of x. Okay? All right, now think about what the domain and the range of this would be. It's the inverse of an exponential, right? So let's review. Let's give you an example. Something real simple. Y equals 2 to the power of x. Okay? All right. 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power, 4. 2 to the negative first power, 1/2. 2 to the negative second power, 1/4. Okay, so here's the graph of the exponential, y equals 2 to the power of x. What is its domain? Domain is all reals. What is its range? Everything greater than 0, not including 0, right? Because we have an asymptote here. Okay, there's an asymptote at the x-axis. So we'll say 0, non-inclusive to infinity. All right, so think. We have a property of inverses. We are supposed to be able to reflect that graph over y equals x to create the inverse function, right? And the nice thing is this is 1 to 1, so when we reflect it over, that inverse will be a function as well. So think if we go down to here, 0, 1 becomes 1, 0. Let's pick a different color, actually. 1, 2 becomes 2, 1. 2, 4 becomes 4, 2. Negative 1, 1/2 becomes 1/2, negative 1. Negative 2, 1/4 becomes 1/4, negative 2. There's the graph of our inverse. And we'll come to know that would have the equation y equals log base 2 of x. Okay, so what does the domain appear to be of that? 0 to infinity, right? Which it should, because that comes from the range of the inverse. Now, what is the range of this logarithmic function? All real numbers, right? Okay. So first thing we're going to do is just work on converting back and forth between what's considered logarithmic form and exponential form. Okay, so here I have 9/2 is equal to 3. That's considered exponential form. In log form, that would be log base 9. Notice I write the 9 as a subscript of 3 equals 1/2. Log base 9 of 3 equals 1/2. And there's always a circular pattern at play here when you're converting from one form to the other. Always start with the base. So think in an exponential situation like this, the base is what's being raised to the power, so it would be 9, right? So that becomes the base of the logarithm. So log base 9 of 3 equals the power of 1/2. And what I want you to really notice there is, look what the logarithm equals. The 1/2 is the exponent from the exponential form, right? Logarithms are exponents. Okay? Understand that. A logarithm represents an exponent. The quicker you wrap your head around that, the more you'll be able to understand the properties that we're going to look at later. All right, so 3 to the power of m equals 12. That's log base 3 of what? Should I put an m there or a 12 there? 12 equals m. So again, there's a circular pattern. I start at the base. Log base 3 of 12 equals m. Okay. Below, I go in the other direction. Log base 4 of 1/16 equals -2. Start at the base. What number is the base there? 4. Start at the base. Raise it to the power of -2 equals 1/16. Is that a true statement? Absolutely. Okay, 3/2 equals log base 5 of 5 radical 5. So here the base is 5. Now we would rotate in the clockwise direction, raise it to the 3/2 power, and that would equal 5 radical 5. Is that a true statement? No? I think it is. What's 5 to the 3/2 the same as?
5 radical 5.
That's, well, non-simplified. The square root of 5 cubed, right? Well, what's 5 cubed? 125, right? Which has a perfect square factor of 25 that I can pull out. Yeah, so that is true. Okay. All right, example 2. Evaluate each logarithm. Okay, so understand logs are numbers. They're exponents, right? So they have a numerical value associated with them. So if I said find the value log base 3 of 81, here's a good way to approach this. Treat it like an equation. Maybe put it into exponential form. 3 to the power of x equals 81. What's x here? Not 3. 4. Yeah, so we would say log base 3 of 81 is equivalent to 4. Okay, next one, log base 10 of 100. If I set that equal to x, that's the same as 10 to the power of x equals 100. What would x need to be there? -2. Very good. Log base 27 of 9. 27 to the power of x equals 9. Okay, this one we might want to get a common base. Well, 27 is 3 cubed, so this becomes 3 to the power of 3x. 9 is 3 squared. So 3x would have to equal 2 there. X would then be 2/3. So So log base 27 of 9 is equal to a value of 2/3. Let's go to the one below that. Log base 6 of the square root of 6. If I set that equal to x, put it into exponential form, 6 to the power of x equals the square root of 6. What's x? 1/2. Because the square root of 6 is the same as 6 to the half power, right? Okay, next one and last one here. Log base 2 of -8. Set it equal to x. 2 to what power is -8? Don't say -3. What's 2 to the -3rd power? 1/8, right? 2 to the -3rd is the same as 1/2 cubed. Okay, so what's the answer here? 2 to what power is -8? There isn't one, right? There's no real number that I can raise 2 to the power of that's going to produce a -8. Go back to our first page here. We got y equals 2 to the power of x. Graph there in red. We are not able to get a result that's negative, right? Because of the asymptote. Okay, and the range being 0 to infinity. So here we're going to say that we are undefined. This, don't say no solution. This logarithm's value is undefined. All right, and then that just goes back to, notice here we're taking log base 2 of -8. -8 is called the argument of the logarithm. Okay. We are unable for that to be, x is not allowed to be negative by our domain, right? You said the domain has to be 0 to infinity. So that argument cannot be negative there. Questions? All right, next we've got some logarithmic equations to solve here. Okay, log base 64 of t equals 1/3. So here it's a different part of the log that I'm solving for. I'm trying to solve for the argument here. Well, exponential form would be a good place to go. 64 to the 1/3 power equals t. That's the same as saying the cube root of 64, which is, of course, 4. Log base 5 of 2r minus 3 equals 2. That's the same as saying 5 squared equals 2r minus 3. Or 25 equals 2r minus 3. Add 3, divide by 2. R is 28/3. All right, and then the last one, we're trying to solve for the base here. T to the 4th power equals 16. Okay, we'll take, I'm sorry.
It's supposed to be 28/2.
28/2, thank you. Oops, sorry. What's 28/2? Ooh, that reduces. Nice, thank you. Okay, t to the 4th equals 16 is next. To solve for t, we can take the 4th root of both sides. What's the 4th root of t to the 4th? Just t. What's the 4th root of 16? Technically, it's 2 or -2, yes? However, if we go back and we look at our log definition, we said our base cannot be a negative number. So the -2 should be ruled out here. Okay, your base, in this case t, has to be a positive value, so we only accept 2 as a solution. All right, now a couple special logarithms next. Okay, so a natural logarithm is a log of base, anybody remember? E. And we have a special notation for it. If you see ln in front of a value, that ln represents natural log. Okay? So if I see ln of x, think that's the same as saying log base e of x. Okay, then we have something called a common logarithm. That's a logarithm of base 10. And typically with a common logarithm, you don't write that base. So notice it just says log x here. It's understood that that's log base 10 of x. Okay. It's kind of like if you see a variable without a power on it, you understand the power to be 1. You don't write the 1. Same idea here. I see a log without a base. Context tells us that's a base of 10. All right, so we got some examples that follow with these special logs in there. This is common log of x equals -4. So the base here would be 10. This is 10 to the -4th equals x. And that would be 1 over 10,000, right? Common log of x equals 0.425. So again, the base is 10 there. 10 to the power of 0.425 equals x. Oh, I'm going to need a calculator for that one. Getting roughly 2.6607. So let's approximate, use the approximation symbol there. Okay, one more common log. Base 10, this is 10 to the 6th power equals x squared. Or 1 million equals x squared. I suppose we could just square root both sides here, or we could set it equal to 0 by subtracting that over. And you're going to end up with two solutions here. It's going to be 1,000 or -1,000. Now, you might be tempted to say, oh, the negative has to be thrown out. But in this case, if you look at the original argument, it's x squared. X is allowed to be a negative in this case because it immediately gets squared and turns positive before you evaluate the logarithm. Okay? So I can keep both of those values. All right, below we got a couple natural logs. Okay, natural log of x equals 3. That's the same as saying e to the 3rd power equals x. A lot of times it's common to leave your answers exact in terms of e, but we can approximate this. So e to the 3rd power should be getting 20.0855 roughly. Okay, natural log of 1. So if I treat that like it's equal to x, we're saying e to what power equals 1? You don't need a calculator for that. 0. All right, then we've got e to the power of x equals 5. That's exponential form. Okay, we're going to go to logarithmic form, which you could write that as log base e of 5 equals x. But log base e of 5 should be rewritten as the natural log of 5. And the nice thing about natural logs, our calculators are programmed for them, right? Our calculators are programmed for natural logs and common logs of base 10. Okay, so we should be able to just punch this in. Just find the LN button of your calculator. You're getting 1.6094, hopefully. Okay. All right, let's keep on rolling here. Evaluate the following. Log base 3 of 3 to the 7th. Let's treat that like it's equal to x. So 3 to the power of x equals 3 to the 7th then. If I convert that, what's that mean x is? 7. All right, so notice the base of the logarithm and the base of the argument were the same here. They were both 3, right? So in that case, they effectively wipe each other out, and you're just left with the power. So in general, log base b of b to the power of n would equal n then. 2 to the power log base 2 of 32. Well, a couple ways you could look at that. What's log base 2 of 32? Somebody said it. 5, yes. Okay, log base 2 of 32, that means 2 to what power is 32? 2 to the 5th power is 32. So I substitute that 5 in for the log there, and then 2 to the 5th is 32. Okay, oh, what do you notice? That's the argument of the logarithm that was in the exponent, right? Okay, so in general then, what do you think b raised to the power log base b of n is? Just n. The bases effectively wipe each other out there. Okay, so with that in mind, we can finish with example 6 here. We've got f is an exponential function equal to b to the power of x. And then g is a logarithmic function, log base b of x. So I want to compose the two. F of g, that would be f evaluated at log base b of x, right? So I'm basically taking that function and I'm substituting it in right there. So that's going to give me b raised to the power log base b of x. Well, as we just saw from the previous example, since the base of b is the same as the base of the logarithm, they effectively wipe each other out, and we equal x. G of f of x would be g evaluated at b to the power of x. That would be log base b evaluated at b to the power of x. And that just ends up equaling x as well. When two functions compose to equal x, remember, that means they're inverses.